temp heat pump applications for space heating and domestic hot water panel. I'll let the panelists introduce themselves, but I am Austin Crosby. I'm an energy engineer and project manager for LaBella Associates. We are an architecture and engineering firm based out of Rochester, New York. My team works on a lot of energy consulting, MEP design, construction management. We work on a lot of feasibility studies, construction projects, and retro commissioning. So we have a lot of experience with heat pumps and a lot of experience with building retrofits. So oftentimes when we're looking to retrofit an existing, maybe a residential building or commercial or even a district system, the existing hydronic equipment is all sized for higher temperature hot water, like 160, 180 degrees. So some people may view this as a barrier to geothermal systems, thinking that geothermal can't reach those temperatures. But our panelists today see this barrier as more of an opportunity to implement their various products to meet those higher temperature waters, provide the thermal energy for the building without having to retrofit the whole building, which can be fairly costly. So with that, I will pass it off to Chris from Nyle, who will talk about his products. Thank you.
Thank you, Austin. I'm Chris Ebener with Nyle Water Heating Systems. I am the president of Nyle Water Heating Systems, but that's not why I'm here today. I am a mechanical engineer and have been in this space for a long time. And I'm open to all sorts of questions, whether it be about high temperature heat pumps, refrigeration engineering, etc. So happy to talk afterwards if anyone has any questions. So Nyle manufactures purpose-built water, air-to-water and water-to-water heat pumps. Here today, I'm here to talk about water source, obviously, specifically for high-temperature water heating. We have modular, standardized equipment for these applications. I know a lot of people in this room think that this is novel or new, and the fact of the matter is that it is not. Nyle has been building high-temperature heat pumps in Maine since 1977. We are here to support you, and we have been doing this for a very long time. If this is the first time you're hearing about us, I'm sorry. This will not be the last. We specialize, though, in manufacturing these heat pumps that produce 160 and above. So if you need hot water, typically, we classify 140 and above as our sweet spot for heat pump engineering and the various applications that fall under those temperatures. So in preface for the other folks that are going to be up here as well, talking about a myriad of technologies in this space. We will be talking about both space heating and domestic hot water and commercial applications. Once you leave the residential realm, typically domestic hot water is going to be required to store at 140 and above to satisfy building code. That is a health and safety thing and is not something to shirk away from. We do need to be able to satisfy those demands. So what does Nyle do? There is a lot that we do with our products. There's a lot of features, a lot of functions, a lot of things there to make your lives easier as designers, as contractors, as engineers. And I don't have enough time today to get into all of it, nor do I have time to get into the nitty-gritty of engineering, but know that we are here to make this as easy as possible for you. Some notes here that we are made in Maine. We are Build America, Buy America qualified. For those that are looking for those extra points on their geothermal projects, we do qualify under that standard. So from a product mixture standpoint, Nyle does have multiple heat pumps for these applications. Specifically, our smaller series, C125W and C185W, our numbers are very easy to understand. Those are the nominal BTU ratings of these units, so 125,000 and 185,000. These units are compact. They're zero top clearance, so they can be stacked for those specific mechanical rooms that are quite small. As we know, footprint is everything in construction, especially in commercial construction. So these give you that viable option. All products from Nyle are tested at the conditions necessary for their operation. So if you have an application and you look at one of our submittals, this is all information off of our website. That data, the capacities, the COPs, the temperatures, those are tested at those exact conditions and are published as they are. Fully built, all inclusive of your pump power and everything else that's included inside of the unit. If you were to do air source with us, that would also include things like defrost and fan power. So we are here to be transparent and give you all of the information that you need in order to design these into your projects and know what performance you're going to get from them. We also publish our LWT curves. As you can see, this particular unit is a very flat 160 degree leaving water temperature for most of its operating range. Once it gets to the bottom, it starts to derate a little bit down towards 140. But does give you that maximum LWT for the majority of its operating condition. And just an example project here for you of these units in the field here in New York, actually up in Rochester. I did go looking for a project a little bit closer to New York, but they are a little newer. This particular project, East End Lofts, you've got a 66 unit apartment building, partially low income. It's actually focused on being an artist community. And this is a GEO system utilizing these units in place of it was originally designed for a cascade system. We implemented these for direct domestic hot water. And these provide all of the domestic hot water for this building. They are 2 single pass units, so I think the last presentation may have led people to believe that variable large delta T is something that's exotic and brand new. And I know for a fact that most of the people up here that are going to talk to you today all offer units in this space, and I've personally been shipping units for about 7 years that do that. So single pass is what it's called. That is a viable option for domestic hot water generation, basically producing set point water for your application. This particular system has 2 single pass C125s paired with 960 gallons of storage and a swing tank. We also offer our water modular series. This is the C270, so this is 270,000 BTUs. What's unique about this unit is it is 0 side clearance, so we're not gonna stack these on top of each other, but when you get into large arrays, I'm currently about to start up a unit for Walt Disney World, where we have 14 of these units providing domestic hot water for a resort. These units are high capacity, designed for that modularity, and we have cascading controls to allow us to control up to 50 of these inside of a single control system, so very large loads. When you want to use more than one, we package them up. We can package up to 5 on a single frame before they get a little ungainly, and you get single point power and single point controls when you do that. So again, same thing, fully transparent. All of the documentation you need to specify these units is available on our site in multiple different configurations. So both single pass and multi-pass up there on the screen. So if you want to do single pass or you want to take return to primary and handle recirc loads directly, these units can do that as well. And this is a project called Civic 66. This is a little bit outside of the area, but wanted to give a reference point for a very cold climate where GEO is really taking off in Ontario. This system's been in place since 2023 and provides hot water for 170 residential units, utilizing 4 of these C270s with 950 gallons of storage. And these are in multi-pass, so they are taking in the recirc loads for the building in addition to the primary domestic hot water load. And I bring this up, multi-pass versus single pass. Also, you'll start hearing the term return to primary, where we bring recirculation back to primary storage. This is a study on a building in Seattle that utilized a water source heat pump of ours to provide domestic hot water to an event center, traditionally not a building that many people work with, but with a very unique domestic hot water signature. But this particular building, they were on a performance contract in order to reduce the energy intensity of the building. And what you see here, if you can, get out your binoculars and see on the far right hand there, the very last black arrow, phase 2 substantial completion by Nyle. They completed multiple energy efficiency upgrades on this building, including lighting, replacing the existing water source heat pumps, adding in air curtains and some other things. And then you see some marginal improvements in the EUI, but it wasn't until the domestic hot water heat pump came online in return to primary that this system used drastically less energy per square foot. So the baseline was 90 EUI, and as of the reporting here, in the middle of the winter, we dropped that to 65 EUI for the whole building, including reducing their reliance on natural gas for domestic hot water heating. So a huge improvement overall in this system. And again, very short window in time here for me to be commercial. So again, if you have any additional questions after this, we manufacture both air and water source commercial heat pump water heaters in North America for the North American market. And we're here to support you from design all the way through commissioning and beyond. So that being said, I'll go ahead and we'll have the next person come on up.
Good afternoon, everybody. So my name is Gannon Dubay. I've been with Trane. I'm sure most of you, or probably all of you, have heard of Trane and are familiar with the company as a whole. I'm out of the Rochester office, but I lead our team across upstate New York for what Trane refers to as sustainable systems. So kind of anything that goes beyond just your day-to-day chilling and heating. And so this includes things like thermal storage, as well as these high-temp hot water systems. So I'm going to touch briefly on single lift machines. As some of these other gentlemen have already kind of explained and will be explaining how some of this stuff works and the benefits of using these. But the reason that high temp hot water is kind of a challenge when you think about geothermal, or even on the air source side when you think about a cold climate, is really the lift requirements, right? Using 0-degree air or 32-degree water and then trying to lift that over 100 degrees and produce 180-degree water is really difficult for your traditional HVAC equipment, okay? And so while we do have some stuff that can meet those needs that I'm going to touch on briefly here, I'm also going to end my short time here by talking about an alternative to that option where we kind of break that lift into. But before we get to that, let's talk about what I like to call our single lift options. On the domestic side, Trane has a partnership in the United States with Mitsubishi. Many of you may already be aware of this. And so on the air source side, we partner with Mitsubishi to utilize some of their hyperheat offerings to provide hot water for domestic situations. So for our really small residential size things, we have what we call the EcoDan, produces just about 160-degree water. And this is part of the hyperheat family, so it's got vapor-injected compressors that can operate well below zero. Very suitable for our northern climate. Once we get into those larger systems, we use what we call the Heat 2.0 product, which is a larger, more of a commercial offering for apartment buildings, hotels, larger buildings, things of that nature. And this is an air-to-water heat pump, and one of the cool things about this machine in particular is the refrigerant that we use is actually CO2. I believe one of these other guys is going to talk a little bit about CO2, so I won't go into the benefits of that right now. But the reason you're not going to see CO2 in your normal chillers, your normal rooftops, your typical comfort cooling, heating, and heating equipment is because it does really well with high lifts. So if you've got an ice rink where you need really cold glycol, or you're trying to do domestic or hot water where you need really hot water, CO2 is great for that application. And you're going to see a lot of products in this space that use CO2 or similar refrigerants. And because this is a domestic hot water heater, it never needs to make chilled water. It's always trying to hit that high lift. And so we're using CO2 as a refrigerant. Now on the water side, I know most of you are here because it's a GEO conference and want me to focus more on the water side. But my friend Chris here actually talked about our product as well, because one thing Trane is really good at is making friends, both at the corporate level as well as at the personal level. And so we have a corporate agreement with Nyle, and so we kind of both have the same offering. So everything that Chris presented is also kind of available through your local Trane partner as well. Excuse me, I shouldn't say everything you presented, but the water source domestic product. Now on the space heating side, we've got a kind of a similar landscape here. So with the smaller stuff, it's actually the same product that we use for our residential, the Mitsubishi EcoDan. On the larger products, we just came out with this EcoDan CAHV. So this is our air-to-water heat pump that we're going to be using for space heating, right? A little bit streamlined. The Heat 2.0 product from before is really made for domestic. It has a double-wall heat exchanger and some other things that make it applicable for domestic. This is more of a standard product that has a single-wall heat exchanger. Once again, we can make some pretty hot water below zero, and I'm sure that'll be getting down to -22 pretty soon. Now, last but not least, on the single heat options, I want to briefly talk about our water source space heating options, which would be Oilon. Once again, this is another product that Trane has decided to form some partnerships on. So Ian, who's speaking after me, is actually going to go pretty in depth on this product line. But this is a bit of something interesting, a little bit different than what you're typically used to when you talk about HVAC, at least in the modern era, because it uses a different sort of compressor that we haven't seen in a while, and that's a piston compressor. Okay. And this allows us to get very wide operating maps, which are really helpful for maintaining stable flow and stable operating when we're talking about these really high temperatures on the load side, upwards of 200 degrees, while using really cold temperatures like geothermal type temperatures on the source side. And one thing that the Oilon product line allows us to do is we're not just taking things off the shelf at this point, we're actually designing the equipment specifically for your application. So one of those options is the refrigerant itself, right? Unlike some of these other products where we just say, hey, here's what the refrigerant we use and here's why we use it, with Oilon, you've got options. We've got a whole menu of refrigerants. Right now, there's about 5 that we typically pick from. And what we're going to look at on a case-by-case basis is what are the lift requirements, what are the flow requirements, what are the temperature requirements, efficiency requirements, all the aspects of your project that are important to you, what's the budget, what's the efficiency we're shooting for, and we're going to pick the right refrigerant that offers the best solution for that. All right, so 3 of the most commonly used refrigerants that we use are right up on here. You can see R450 offers, in most cases, the best COP. So if we're doing an efficiency-driven project, there's a good chance that's where we're going to land, right? 513A gives us the best capacity per given footprint. So if we have footprint restrictions or just first cost restrictions where we're trying to minimize the amount of metal that we have to buy, right, we might end up on that refrigerant. Or 515, for example, if we really need to get above that, up into that 180 or higher degree water. Now, as we think about this and we kind of start thinking about, instead of pulling stuff off the shelf, what if we take a step back and really figure out what's right for the system? I'm moving to my last point here, and I really want you to kind of mentally zoom out even farther and think about not just what product is right for the job, but what system makes sense, okay? Can I get a show of hands who here has heard the term heat pump? I would expect almost everyone in the room is going to raise their hand. Okay, yeah. Now, how about, have you heard the term chiller heater? Okay, a few of you, but certainly many fewer hands. And so to talk about my last topic here, I first want to define this term. The term heat pump is a great term. Everybody uses it, and we all know what it means. It's a machine that has a compressor that makes usable heat. But when we start talking about different types of machines and different types of systems, there's a lot of different functional products, a lot of different functional technologies that all kind of fall under that umbrella. And so we find it useful to kind of categorize those and kind of split those up a little more. So when Trane refers to a heat pump specifically, we're going to have something that's got a reversing valve in it. So for your smaller distributed systems where you got your little 2, 3, 4 ton heat pumps all throughout the building, that's what we're going to refer to as a heat pump. Or a smaller scroll chiller that has a reversing valve in it, we're going to call that a heat pump chiller. But for our larger systems, like our central geothermal plants and our multiple hundreds, multiple thousands of tons of cooling, right, it starts to become not economical to put giant reversing valves on those machines. And what we tend to do in those cases is we use what's a more traditional cooling chiller that's used to making cold water and making hot water in a condenser. And we just do the switching on the hydronic side, right? So the machine itself is functioning just like a normal chiller and is actually built pretty much exactly like a normal chiller, but with a little bit of a controls upgrade that allows us to control to that hot water temp. And then if we need to do any changeover, that's all done on the hydronic side through valving. Now, pretty much any chiller can be used as a chiller heater, but since I'm here today to talk about high temp heat pumps specific, I want to show 2 of Trane's rock stars, as it were, as far as getting these higher temps. So for our more medium-sized projects, kind of below that 10 million BTU threshold, we're going to be using the RTWD or the RTZA, and these are our screw chillers. If you're familiar with Trane products, you've probably heard of the RTWD at some point, because we've been making this since the 80s. And really the only difference is we're now allowing it to control to a hot water temperature, or if you need to go over 165, we're just going to swap the refrigerant out. Okay? But these are the same machines we've been making for 40 years. If you go to a K-12 school and you're trying to get them to bite on this whole electrified heating thing, you can sit there and explain these exotic or these brand new machines that make 200 degree heat, but it uses this special compressor, or you can just give them another machine that looks exactly like the one they already have in the building. Right? So what we're able to do is produce these hot water temperatures using more traditional HVAC equipment. And on the bottom here, you see our centrifugal chiller. I looked it up. We've been making this chiller for 82 years. Obviously, as the years come, there's been upgrades, but at its core, it's the same machine, it's the same parts and pieces. So people are familiar with this equipment. And we're able to do up to 180 degrees on that machine. And what this allows us to do by using more standard equipment is doing what Trane calls a cascade system, right? So our initial challenge by using a cold source temperature and making hot water is that incredible lift, upwards of 100 degrees, as high as 180-degree lift, right? And traditional HVAC equipment can't do that. But if we split that lift requirement in two and say we do a low temp machine that's doing 90 degrees of lift and a high temp machine that's also doing 90 degrees of lift, now we're achieving our total lift, but we're able to use traditional HVAC equipment that's optimized and zeroed in on those operating maps. All right, and this is a very simple system diagram of what that would look like, both for an air-cooled as well as a water-cooled, in this case, geothermal sourced project layout, right? Now, why does this make sense, right? What are the benefits of here? Why would we do with 2 units what we could do with 1, right? Well, first of all, this really only makes sense for larger systems, all right? If you're in your 200 tons or like 1 million BTUs of heating load, right, the added complexity of controls that's gonna be required to implement a system like this, the juice probably isn't worth the squeeze. And I would encourage you to use one of these more, single thing in a box type products. But when you start getting into these bigger systems, right, those costs really add up. You get these modular products where now you need 30, 40 modules, right? Or you get these more specialty industrial type heat pumps that are really expensive. You see the dollars per ton on that, and it's astronomical compared to a more traditional chiller. And so when you get into those larger sizes, suddenly that controls complexity becomes a drop in the bucket, and the equipment cost scales much, much better with size. Okay. Also, and I already touched on this, we're using more standard equipment. So if you've got an owner or a service organization that's already used to servicing screw or centrifugal chillers, this is just adding to their repertoire. This is just another machine they have to service. There's really nothing new for them to learn. Okay. Also, by splitting this up, we give you access to this kind of intermediate loop. We call it the energy transfer loop, and that's that loop that goes from the condenser of the low temp machine into the evaporator of the high temp machine. And that's typically a lukewarm loop, like 90, 100 degrees, somewhere in there. But this allows you to do a lot of heat recovery. So if you have any other heat sources besides your primary, we can tie right into this loop and feed all that to your high temp machine, right? This could be geothermal, this could be wastewater heat recovery, it could be cooling loads in the space. There's really a lot of options, and it offers a lot of flexibility, okay? Utilizing existing infrastructure is another thing. So if you've got a building, they just put brand new water-cooled chiller system in 5-10 years ago, and now you're coming in trying to get them to go to a high-temperature heating application, instead of ripping out those chillers or abandoning them in place and putting a whole new system on, we can use that existing equipment as the low stage, and all we need to do is add that high stage. So we're really only adding half of the system to what they've already got existing, okay? And stepped on the cord. There we go. And last but not least, it also offers some redundancy, right? Because these are all just traditional HVAC chillers, if you just add a little bit of piping down in that right corner, let's say you have a system like this where you really only have 1 low temp chiller and 1 high temp chiller, right? And let's say it's the middle of summer, the hottest day of the year, all of a sudden that low temp chiller goes down and you've got no cooling in the building, all right? With a little bit of forethought, a couple extra feet of piping, you can pipe that intermediate loop down into that chilled water loop ahead of time, and all we need to do now is just bypass that flow around, and we can use that high temp unit as a redundant cooler and use that to create our chilled water in that emergency case. So, last but not least, I just have an example here to show this in practice, so you can kind of believe me when I say that you can actually have a lower first cost by splitting this in half. This particular example happens to be air source, so please forgive me. I do realize this is a GEO conference, but the concepts transfer over regardless of what the source is. So in this case, we're using a cold ambient temperature of 0 degrees on the outside, right? And we've got a heating load of about 4.2 million BTUs, all right? We're gonna give us 0 coincident cooling load, so make it as hard as we can to source that heat, right? And we're gonna try to do, in this case, 160 degrees water. Now, if you were to do this, what I would call the blunt force method, brute force method, where you wanna do this with a single machine or a single bank of machines, right, this is essentially specialty equipment to take 0 degree air and make 160 degree water out of it. It exists, Trane has products that do this, but at this size, you're gonna need, in this case, it looks like 40 modules in order to hit that, right? Modular equipment is not cheap, and it takes up a lot of space, especially on the air side. And so if you were to add up those 40 modules and what it would actually cost to hit that capacity, it'd be around $6 million for the heat pumps themselves. Now, if you take that same condition, those same exact conditions, the same loads, and you split it up into the system diagram that's up on the sheet here that shows just a standard air-to-water heat pump on the outside as your first stage, and a standard chiller heater on the inside, right, we can reduce that cost to about half. Because now we're operating each of those pieces of equipment in those highly optimized operating maps that they were designed for, instead of selecting equipment at the limits of its capabilities and trying to force it to hit the temperatures we need. So, we have a booth over this side on that side. If you have any questions for me or any of the Trane folks after the fact, please come see me. Please feel free to take a screenshot of my contact information, or if you're here locally in the New York area, please, you can contact your local Trane account manager. Thank you, everybody.
Exactly. All right, what's the volume on this thing? Hello, everyone. My name is Ian Motley. I work at Miller Proctor & Nicholas, which is also now part of a bigger conglomerate owning a company called Mobile Steam and Hudson Clean Heat. I want to thank Chris and Gannon for making you all experts on high temp heat pumps so I can talk about more complex ideas with you guys. We are located in New York. We have 3 offices, and a lot of what our offerings are on designing solutions. Miller Proctor & Nicholas is a 60-year-old boiler company, and we specialize in hydronic and 1- and 2-pipe steam systems, even going into high pressure. And so after acquiring Mobile Steam, which is also a very old company, we've now, through the developments of Local Law 97 and all the electrification and decarbonization efforts, started a company that is a tailored solution towards those. So we really want to hold the hands of all of the stakeholders through the process of everything from the technology to the rebates, to the permitting, to the general contractor interaction, because we know it can be really painful to go through all of that. As Gannon introduced, one of the major equipments we partner with, and I really want to highlight today, is the Oilon chill heat pump. This, for us, was a really natural connection and partnership. They're based out of Finland, and they are also close to a 60-year-old company. They also did boilers dating way back, and so heating is in their blood and it's in our blood. And so there's a really good synergy there. We're employee-owned, they're family-owned, and we're roughly the same size. So these heat pumps are water to water. In discussing that, the automation is all built in, and so these can really be coupled with anything, and it's very important to think of it as such. I know in the industry it's really common to hear things like geothermal heat pumps. I always have a bit of an issue with that because it's kind of a misnomer. Yes, you can use them for geothermal, but anything that's a geothermal heat pump could also be used for other things. These are modular in design, and they also are capable of having different types of compressors, which we're going to talk about a little more. All of them on the P-Series side for high temp can fit through standard doorways, and that's kind of how they measure them. And they're also designed to be extremely simple to work on. So anyone at any building will be able to do maintenance on these. As discussed before, and especially as things go on, refrigerants, those are almost becoming as important as gas and oil. The GHG emission requirements and the reporting requirements on buildings, especially in New York City, are becoming so strict and so changing that you can no longer leave the selection of your refrigerant for your equipment out of your consideration. For the Oilon heat pumps, as far as temperatures below 190, so all of these are high temperature, we have everything from, and pretty much all A1s I want to start. Oilon does offer A2Ls, and they do offer butane and propane for the European markets, but in New York, we're really pushing just A1s. So you have 450, 513, 1234, 515B. What you pick on these, as Gannon said, will really matter on what you consider for, are you really capacity focused? Are you at a certain temperature predominantly over another one? Are you really concerned with your emissions? Because you might be willing to sacrifice some COP or capacity in order to get a better GWP or a better ozone depletion. Then I want to highlight on the top, the piston compressor units allow for a higher lift. So we use 1233 ZD, which is a very low pressure refrigerant. So you're not going up to like 600 PSIG, you're not going into crazy ranges. and you can get up to 260 degrees Fahrenheit, and we're increasing that at the factory, but I've been told to leave it there. What that does let us do is get up to 15 PSIG steam. So I won't just be covering hot water, domestic hot water, we're covering high temp hydronic, and we're covering low pressure steam applications. Now that you guys are graduated, you've had 2 people tell you about heat pumps, I want to get a bit more into COPs. They can be misleading and hard to grapple with. When heat pumps are operating, COP is a measure of the useful heat you are being provided from the heat pump in comparison to the electricity it is taking to run the heat pump. It's important to think of it that way. Sometimes, when 2 numbers you can get actually, you can get COP heating and you can get total COP. It's important to remember that because these are simultaneous products. If you start hearing numbers from people that COP of 9, COP of 10, they're probably telling you the combined COP. If you're getting numbers like 3 or 4, don't be like, oh, that's a bad heat pump. You're getting a realistic heating-only COP. Another important factor, and you'll see from these trend lines, as the COPs drop, depending on what the temperatures you're working with, capacities will also change. So if you are given a heat pump that's rated at 200 MBH, and you change the temperatures that it's working with, you will also change the capacities that are available from that heat pump. To put COP charts in perspective for customers or people who do not want engineering terms, the red line on this chart is an emissions line. So anything above that, you are beating emissions of a gas or oil-fired equivalent. The green line is where you're starting to become financially efficient. So that will be local to your area. You did that green line for New York City. Electricity is not cheap in New York. So even with high COPs, in order to be financially equivalent on your utility bill, you do have to hit a pretty high mark. And it's important, I think, for customers to see where that is on these charts with this equipment. That being said, COPs are instantaneous ratings and factory conditions. It is important in these design considerations to take a nuanced approach into what the annual loading for a building will be like. What can I do to design the system that will change those effective COPs to fit my condition? So I would heavily encourage anything like a seasonal COP or different conditions when you're talking to your equipment manufacturers on what they are giving you. The brochure COP is not what you will see throughout a year of operation. Speaking of system design, I know diagrams like this can look scary. I tried to make it simple and not like an engineering diagram. Speaking of the cascade approach Gannon brought up, it is important to know that these systems add some things that don't, I think, get highlighted on a balance sheet or on an install cost sheet. One being redundancy, resiliency. By adding more equipment to do the same functions, you can really make a system more robust and better at doing its specific targets instead of having one piece of equipment try to meet all of the needs of a building. Another important factor is, and depending on the building you can have space heat, you can have domestic, you can have chilled water, and they will not match up almost ever. You're not going to have the same amount of chilling required as your domestic hot water. You're not going to have the same amount of space heat. And whether it's winter or summer, again, they will have peaks, and some might even be zero. And so making sure your equipment is designed for the case it's being used and not just plugging an equipment into just any use and expecting it to work. A lot of things can happen in the industry where equipment and or a way of making systems gets a bad rep because it was incorrectly installed, designed, or commissioned. And it's important to know that. Part of our approach, and an approach I'd use in general, look at the whole building or look at the case. If you take a 300 boiler horsepower plant or a large domestic water load and you have not checked for leaks, you have not checked for tenants who just run their water all day, you have not checked for what's available, and you try to replace it with heat pumps, you will have a harder time than you need to have. Focus on checking your envelope, checking your usage, doing proper monitoring, and then attack these high-cost initiatives. Part of what we do, a little bit of pushing, there is education available. There are opportunities to go see these. Anyone I know who's worked on a project, and I'm sure Gannon, Chris, and Geoff will agree, we're happy to talk about it. No one's going to charge you to ask a question or answer something on equipment. We do it in New York. It's something our company focuses on. So now let's look into some pretty designs of systems. Domestic hot water. So this is how it could look. And I don't know if raising your hands, is anyone here all New York based, working in NY-GEO buildings, multifamilies, co-ops? One benefit that again is hard to see on the balance sheet in the beginning of a project is how much nicer a system will be if you upgrade it. I've worked in and seen these boiler rooms. A lot of them are in really rough shape. So that is something that can be added for the people who don't work in them every day, are making the design decisions and the financial decisions. Remind them, take them down to the boiler room, let them see what it's like. Geothermal, solar hot water heating, air source heat pumps, dry air coolers, all of these are parts of these solutions. So when you're looking at the equipment, when you're going to Trane or Nyle or any of these companies, don't only ask about the water source heat pumps. Make sure you're also thinking about the accessory equipment and how it's going to fit in. Specific to what we're targeting in New York, steam retrofits. Pretty much the same info I'd have for the other one, right? You're looking at air source heat pumps, maybe cascading water source heat pumps, geothermal, condensing boilers, all part of what can feed a high temperature heat pump. So these steam producing 250-degree units. A thing I'll add is we do not look for any given approach. We're not trying to push anything. There are many buildings that have ideally 2 or more boilers, and you can use those as a great instance to partially electrify. When it comes to building loading, it is very rare that the design load is 100% of the year. Normally you have a couple weeks each year where that design heating load is being hit, and then you've got 3 to 4 months where you have 0 heating load, and then another 4 or 5 months where it's going to be about 10 to 30% of the heating load. If you install heat pump systems to meet those loads, you will see great returns. There are individual cases where you can fully electrify, and this is possible with high temperature heat pumps. Oilon definitely up to 15 PSI for 1 and 2 pipe applications, and that can completely remove a building's reliance on gas, even for 2 and 1 pipe steam. This can be done through quite a few different types of equipment. Oilon is kind of our top one, and then we have multiple manufacturers for clean steam generators and coiled tanks, which can be doubled to produce domestic hot water without requiring the need to make steam, which is one of the things that a lot of these buildings face, is the requirement where they use their boiler in the summer to make domestic hot water, which is creating a lot of gas use that is not needed at that time of year. From that, Geoff, I'm going to pass it up to you.
Thank you, Ian. Good afternoon. My name is Geoff Cullen. I work for GA Fleet. I've been with them for 14 years. Similar to Miller Proctor Nicholas, we are a manufacturer's rep here in New York City. We're about 150 people strong. About 70 of us are on the design, new construction side, like Ian said, helping out with design consultations, product selection, just basically being a resource to the community for sizing, selection, and engineering sources. Our other half of our company is based mostly in service. So we like to see our products go in cradle to grave, basically starting with the original design and then servicing them through basically their life throughout that building. I'm here today to talk about one of our brands, a company called Link. Link makes a CO2 or R744 heat pump. I think the rest of the panel here has done a great job of establishing the fact that we can certainly make high temperature hot water with many different technologies. We've also touched on both how you can do that for space heating and domestic hot water. I wanted to take the approach today of kind of dialing in a little bit about domestic hot water specifically. I think in the past presentation as well as up here today, we can certainly say that in many cases domestic hot water is kind of the low-hanging fruit for a lot of buildings in terms of electrifying. So we are seeing in a lot of buildings that being kind of the first load to be electrified, and oftentimes a little bit easier to digest and actually implement. And I wanted to speak specifically, certainly in the context of water source and air source, but as well in the context of New York and specifically New York City, why we felt that partnering with a company like Link and CO2 specifically was the right choice for New York City specifically. Link is a sister company. It's owned by Watts, that many of you may know from backflow preventers, valves, things like that. Link falls underneath their applied science, applied engineering tenant. They're also sister companies, the PVI and Airco. Both have a long history in domestic hot water. So while a new brand to the market, certainly with a lot of expertise in terms of the application, I think it was the last presentation, somebody said that you have to treat domestic water, especially with heat pumps, very specifically. It is not like space heating, and that can't be more true. So definitely agree completely with that. So with that, some benefits specifically about CO2 or 744. Like most of us have said today, you can certainly get very high temperature water. 180 degrees, typically at a minimum. You can certainly push that up to 190, 190 plus, but in many cases, honestly, regulating bodies like UL and some of the other certifications actually limit us to how high we can actually push those temperatures. So certainly well within the operating conditions of the refrigerant. Your COPs, I did a great job, Ian, talking about COPs and some of the fallacies or misconstructions of them. We're typically going to be seeing with CO2 1.9 up to 5, again, if you're doing kind of simultaneous heating and cooling. But typically for R744, you're going to see equal, if not slightly better, COP performance compared to a lot of other refrigerants out there on the market. So no penalty hit there, and still very efficient and can certainly be affordable from a utility standpoint. On the source temperature side, we also are able to accept a pretty wide range of source temperatures. So from a GEO or a water source perspective, we can see as low as 18 degrees source water all the way up to about 130 degrees source water and still operate completely at full capacity with very minimal hits on COP and reliability. For the air source variants of our products, you can go down to -4. Truthfully, probably similar to Mitsubishi, lower than that. It's more so a restriction of air chambers and testing facilities to see if we can push it even lower. We had 0 issues with all the products that we have out installed this year, one of the coldest winters we've had here in New York in a long time. And then for our hotter climates, you can go all the way up to 113 degrees. So a pretty wide range and certainly well within the limits of what we see here, specifically in New York State. Another benefit for CO2, all heat pumps are going to increase or decrease their output depending on what your source temperatures are. So the warmer they are, the more output you get. The lower those source temperatures, the less output. However, what you'll see with many refrigerants is the outlet temperature will also decline with lowering source temperatures. With CO2, we're able to maintain a consistent outlet temperature regardless of source conditions. So we can always design for that 180 degree outlet water regardless of what our source temperatures are going to be. So that helps us when we're trying to design the storage elements of the overall system. Because we're able to store at 180, you may ask, why are we even doing that? Here in New York, space is king. I think everybody knows that. Being able to store at 180 degrees allows us to use less overall storage. So as you can imagine, you're going to get more BTUs per gallon at 180 degrees than you would at 140. That's going to allow us to reduce the overall storage capacity in most of our systems by about 25%, which is going to save space as well as first cost. The other advantage there is also going to be Legionella mitigation. So as Chris mentioned, for us in commercial aspect, we're typically going to be storing at least 140 degrees to mitigate against the propagation of Legionella. At 140 degrees, I think Legionella multiplies every 2 minutes or something like that, certainly within health and safety standards. At 180 degrees, we actually kill the bacteria instantly. So an added benefit there that Legionella is almost completely eradicated from the idea that we have potentially hundreds, if not thousands of gallons of stored water. The other benefit is there's for CO2 specifically, there's no special training, unlike A2Ls that we're starting to see propagate into the community and into the manufacturing realm. special monitoring requirements due to the flammability, evacuation procedures, anything like that. So you don't have to go out and get any special trainings or certifications. CO2 is treated just like all the refrigerants that you're probably used to already working with. Not to divide the room here with Peter Luger fans versus A1 steak sauce here. Had a little fun with AI myself. I think it's important to talk about refrigerant and the classifications whenever you're getting involved in the selection of a heat pump. So just a small history lesson on CO2. So in 1850, the first patent was actually produced for CO2 as a refrigerant, so it goes back quite a while. It was used pretty prevalently up until the 30s, primarily on ships, transporting ice, beer, food, all sorts of things like that. And then in the 30s, the great capitalists that we have at GM and DuPont started to advocate for synthetic refrigerants, namely R12 and R22. Those had a pretty good run until the late 80s. They basically ruled the roost in the HVAC automotive market until we started to realize that they had an adverse effect on our ozone. So there's something called ODP, ozone depletion potential. R12 and 22 had very high ODPs. People were getting higher increased rates of skin cancer, all those fun things. So a bunch of countries got together in Montreal, Canada, and decided we need to phase these out. We need to start replenishing our ozone layer. With those, and behind them came HFCs, R134A and R410A, something that basically everybody here is probably very familiar with. And those had a pretty good run as well, about 30 years, until we started to understand the impacts that they had on global warming. Then in 2016, a bunch of those same countries got together in Africa and decided that we want to, if we want to start using more and more heat pumps to electrify our countries, that we're not going to be wanting to be adversely affecting global warming in general, basically taking 2 steps forward and 1 step back by using these refrigerants. So those 2 have gotten banned, and you're starting to see that banned in place now with 410A and 134 no longer being able to be manufactured and then sold in New York State. So that kind of forces us back towards natural refrigerants. CO2 being one of them. I know there's a lot of talk about propane being another, obviously flammability issues there. The beauty with CO2 is it's still an A1. It's been around a long time. It's proven. It's actually the baseline for what GWP is. So it's a GWP of 1. There's very few refrigerants out there, if any, that can actually beat it in respect to global warming. The next part to kind of keep in mind there too is that that cycle that I explained is continuing on. So even the refrigerants that we're starting to see today, 454B, R32, a lot of these A2Ls, they're soon to be banned in New York State as well. Most of them are going to tend to have a life till about 2034, but that's only about 8 years from now. And in some applications like VRF, it's even shorter, 2030. So what's being installed today is almost already obsolete. Whereas if you're going to be using an A1 like CO2, it's been around since the 1850s and it's not going anywhere. So certainly something to consider. You have to really understand the implications of the refrigerant that you're using in your heat pump. Specifically here in New York, there's also a operating engineer's requirement as part of the FD&Y fire code. And that most people that have worked here in New York understand that's basically your 15 horsepower rule. So you can have as many compressors as you want in a building under 15 horsepower with a traditional A1 refrigerant, and you don't have any operating engineering requirements. And that's why you'll tend to see lots and lots of modular chillers, and maybe less so of the chillers that Gannon talked about, when you're talking 1,000, 2,000 ton chillers, unless you're in a commercial office space that already has a bunch of operating engineers working there day in and day out. CO2, thankfully, although an A1 does not get treated like A1s, it's actually, for whatever reason, back when this code was first instituted, treated like A2s, B1s, B2s, a whole bunch of others. It's not relegated to compressor horsepower. It's actually relegated to the amount of refrigerant in the system. at 200 pounds or less. There's no supervision requirement above 200 pounds. You would have the same ones if you're using A1s well over 15 horsepower. And it seems like for A2Ls, we're going to fall into a similar classification, but still to be seen on what the fire department decides to do. So with that, the unit itself, Link Aegis is the name of it. It comes in several different varieties. Because of the use of CO2, we're actually able to get some of the largest capacities in the industry. So we have a nominal rating of 250, 350, and 500 MBH. That's 14, 25, and 35 horsepower. Again, those horsepowers are less of a concern for us here in New York because of the different classification of CO2. For reference, that 35 horsepower compressor only has about 80 pounds of refrigerant, so well under the 200-pound requirement. It comes in 3 varieties: water source, which is probably most prevalent to the people here today, and geothermal applications, air source, and then what I think is pretty interesting is actually a hybrid or dual variety that can be an air source unit that can also run as water source. And we'll talk a little bit more about that. The other thing to consider when you're talking about domestic hot water and heat pumps is certainly an end-to-end solution. So on the HVAC side, contractors, engineers, operators, they're more used to working with heat pumps and refrigeration systems. When you get into the plumbing world, it's a completely new technology. It's a completely understaffed, undereducated community that has never really had to deal with heat pumps or refrigeration circuits in the past. So Watts and Link made the decision to make sure that they can provide an end-to-end solution. So they want to treat this product as any other water heater. So bring cold water in, hot water after the mixing valve out. Everything in between is provided and designed by Watts, by Link, by GA Fleet here in New York. And we were able to lean on that history of Watts, Airco, PVI, to really kind of take advantage of their expertise in domestic hot water sizing to get more aggressive sizings than your typical ASPE or ASHRAE curves, Hunter curves, things like that. So first application here was going to be a water source installation. I apologize, this does not show geothermal. This is more for condenser water. But at the end of the day, similar to what someone said before, ground source heat pump, water source heat pump, kind of one and the same, as long as we have a source of water that we can either take heat from or add heat into. These systems will work. And similar to what we saw in the past presentation, we're going to have multiple tanks typically in series to improve stratification and have a very high lift on our CO2 heat pump. We're typically going from 40-degree or 50-degree incoming domestic water from the street and putting out that 170 or 180-degree water into the tank, so a very high lift. Unfortunately, that is the one benefit, but at the same time, detractor to CO2. It wants a really high lift, so it's a great application for domestic water. Certainly, as Gannon said, maybe ice rinks, condenser water injection, but outside of that, traditional baseboard heating or fan coil with relatively low delta T is not going to be a great fit for CO2. Another interesting application on the water source side and a personal plug. Tomorrow, 10:30 a.m., going to be talking about wastewater heat recovery. I think Gannon also mentioned that one. Gannon, you covered a lot of bases today, so thank you for that. But another great addition to geothermal systems, supplementing it or increasing the overall capacity of a system would be wastewater heat recovery, which you can also use these water source equipment for. Air source, not going to go too crazy into it. At the end of the day, it's very, very similar. You've got the unit outside. The one thing I do like to highlight is the heat exchanger package in the lower left-hand corner there. That allows us to actually use closed loop between the outdoor unit and the storage tanks inside. And some advantages there are, one, we can have glycol there, so we don't have freeze protection issues. We don't have to worry about heat tracing. Two, we are able to control flows. So we talked about in the last one how we're doing pretty high lift, so we have high delta T's, low flow. We're able to segregate our flow rates from the actual domestic water usage within the building through this heat exchanger and control flow through the unit, which gives us better performance, better control, better reliability. And last and certainly not least, I think we all know heat pumps are very expensive pieces of equipment. So by going through a plate and frame heat exchanger, we actually protect the heat exchanger within the unit, the refrigerant to water heat exchanger, from the impurities and the dirt and everything else that we see in our domestic hot water streams. And last, in terms of applications, is the hybrid. And I think this is interesting, especially from a GEO standpoint, is that it can operate as an air source unit or a water source unit depending on the availability of that water source. So from a GEO standpoint, you could decrease the size of the bore fields, decrease the size of the overall system, maybe help some of the finances, and take off that domestic hot water heating load in the wintertime and run this as an air source unit. Or more traditionally, if you have a condenser water system in a building where you're only running air conditioning, say it's an apartment, you're only running air conditioning in the summertime, and you no longer have that rejected heat during the winter, you can run this as a water source unit, take advantage of the higher COPs during the summer when you have all this rejected heat, decrease your cooling tower loads, and then come the winter time, run it as an air source unit to still provide domestic water to the building. I'm going to finish off with an installation reference here in New York, actually a very large geothermal system, 1515 Surf Avenue out in Coney Island. The stakeholders there listed on top. But this is a 2-tower, largest tower is 26 stories, 450 plus apartments, been operational since 2024. At that time in 2024, it was the first and largest 100% geothermal multifamily project in New York City. We were able to actually come in and reduce the amount of equipment due to the use of CO2, as well as increase the overall efficiency. Because of the higher COPs than what was the unit that was originally designed with. Because we were able to exceed that 15 horsepower capacity, we were able to go from 11 heat pumps down to 6, and from 15 tanks down to 8, using about half the amount of storage. Then paired with the better efficiency of the equipment, we were able to save operationally 20% year over year. So a great case study for the use of CO2 heat pumps specifically for domestic hot water and geothermal. For us here in New York, we have about 40 different sites with this equipment installed. That encompasses about 100 different pieces of equipment. And I've linked some case studies there too if you wanted to find out some more. But with that, thank you for your time. Happy to answer some questions. Thank you very much.
Okay. Thank you again to our panelists. I think that was a lot of great information that they presented. So now for the Q&A. Fortunately, we have 0 minutes to answer questions. But if you did have questions, our contacts are on the screen now. Actually, no emails are up there, but feel free to come up and ask any questions you have in person. We'll stick around for a few minutes. So yeah, thank you for everybody for attending this panel. Thanks.